Hello viewers, I am Dr. Gaurav Singh and I am Senior Scientist at Land and Water Management Engineering at ICAR-Indian Institute of Soil and Water Conservation Research Center Vasad, located at District Anand in Gujarat. So friends, today I will be discussing with you the basic understanding of the terminologies and the methods for artificial groundwater recharge. So let us start. So first we will start with the water resources of India with the key statistics and the facts. The average annual precipitation of the country, whatever the amount of rainfall and the snowfall which we are receiving in our country, the total amount of water which we are receiving is around 3,880 billion cubic meters, and out of that 1,999 billion cubic meters goes as a runoff. The utilizable water resources in the country is around 1,123 billion cubic meters, out of which the surface water storage is in the form of 690 billion cubic meter and the groundwater storage is around 433 billion cubic meter. The live storage capacity of the reservoirs in our country is 253 billion cubic meter. And if we see the per capita availability of water in our country, after the independence in 1951, the per capita availability of water was 5,177 million meter cube, and in 2001 it reduced to 1,860 meter cube. Further, in 2011, the per capita availability further reduced to 1,545 meter cube. And it is projected that by 2050, the per capita water availability in our country will further reduce to 1,140 meter cube. And if similar condition exists, soon the country will become water scarce if this per capita water availability goes below 1,000 meter cube. So in the global context, if we see, the India has about 18% of the world population, but only 4% of the fresh water resources is available with the country. And if we see the sectoral use of the water in our country, the agriculture is the prime user. Basically, in agriculture we use the water for the irrigation purpose, and about 80% of the water in our country is used for agriculture, followed by the domestic, that is 10%, and the other industrial and other uses, that is 10%. Now, if we see the groundwater resources of India, the key facts and the status, the total replenishable groundwater resources in the country is 437 billion cubic meters per year, out of which the annual extractable groundwater resources is 398 billion cubic meters. The annual groundwater extraction is 239 billion cubic meter, that is 60% of the available resources. And the major use of the groundwater in our country goes for irrigation, that is 87%, and remaining the 13% goes for the domestic and the industrial purposes. The level of extraction in our country is 60% overall, and it is projected that it is further increasing at the pace of 0.3% per year. And if we see the status of different groundwater units in our country, the overexploited units is around 1,006, that is 15%, and critical or semi-critical units are 880, that is 13%, and safe units are 5,800, that is 72%. And if you see the top groundwater extracting states, so the first one is the Uttar Pradesh, followed by Punjab, Haryana, Rajasthan, Tamil Nadu, Gujarat, Andhra Pradesh. And causes of groundwater decline in India. The first most important cause for the groundwater decline is the over extraction of water, these groundwater resources, for the irrigation purpose. There is widespread use of tube wells and bore wells for water intensive crops like rice, sugarcane and wheat, especially in the northern part of the country. The second cause for the groundwater decline in our country is also the reason for the free and subsidized electricity, which encourages the farmers for excessive pumping and utilization of groundwater resources. The other reasons are also there, like rapid urbanization and industrialization. The unregulated borewell drilling in urban areas is the major concern. There is a declining and erratic rainfall, and this leads to the variability in the monsoon, which reduces the natural recharge. The reduced natural recharge due to the loss of wetland, ponds and infiltration zones due to urban expansion is also a major reason for the groundwater decline in our country. The poor water management and governance, that is the weak enforcement of the groundwater regulation in the country, and the lack of awareness and the water budgeting at the community level is also responsible for the groundwater decline. Further, the climate change impacts are also causing the groundwater decline. There is an increased evapotranspiration and prolonged dry spell reported throughout the country, and there is a decline in the snow melt and delayed monsoon onset in some of the regions of our country. So let us see what is groundwater and what are the factors that affects its occurrence. The groundwater is the water that occurs below the earth's surface, filling the pores and fractures of soil, sediments and rocks, and is capable of yielding water to wells, springs or infiltration galleries. This is the standard definition of the groundwater given by the Central Groundwater Board, Ministry of Jal Shakti, Government of India. Now, the groundwater is basically present in the geological formation that we call as aquifers. So, aquifer is a geological formation, group of formations or part of a formation that is sufficiently porous and permeable to store, transmit and yield significant quantities of groundwater to wells and springs. Now let us see what are the aquifer properties that affect the groundwater occurrence. So the first aquifer property is the porosity. So porosity is nothing but it is the percentage of the void spaces that is present in the rocks or the soil, and it determines the water storage capacity. Next one is the permeability, and it is the ability of the geological formation or the earth material to transmit the water through the pore spaces or the fractures present beneath them. The next property is the specific yield. Specific yield is the portion of the stored water that drains freely under the action of gravity. The next property is the specific retention. Specific retention is the water that is retained in the pores due to the action of capillary forces in the geological formation or the aquifers. Next property is the transmissivity. Transmissivity is the rate of the groundwater flow through aquifer thickness, that we call it as transmissivity. Next property is the storage coefficient. So the amount of water that is released per unit area, per unit change in the head, is called as storage coefficient. The next property is the aquifer thickness and extent. So greater the thickness of the geological formation or the aquifer, there is a higher yield potential of that particular aquifer. The next property is the hydraulic gradient. So hydraulic gradient is the slope of the water table that controls the flow of direction and the velocity within the aquifer and between the aquifer. So let us see the classification of aquifers. So we can classify the aquifers into 4 types. So first one is the unconfined aquifer. We also call the unconfined aquifer as the water table aquifer. The upper surface is the water table and it is open to the atmosphere through permeable material. And it is recharged directly by the rainfall and the surface infiltration. The water level in the well rises to the water table. The next one is the confined aquifer, and it is bounded above and below by an impermeable layer that we call as aquithards. The water is under pressure, and when tapped by a well, it may rise above the top of the aquifer, that we call it as artesian condition. Recharge occurs from a distance outcrop area, that is the recharge zone. Next one is the semi-confined or leaky aquifer. The partially confined by a semi-permeable layer which allows slow leakage between the aquifers through aquithards. The next one is the purged aquifer, and it occurs above the main water table, separated by a local impermeable layer that we call as clay lens, usually small and temporary in nature. Now let us see the types of water bearing geological formation. So first one is the aquifer. So aquifer is a permeable geological formation that stores and transmits significant quantities of groundwater. Here there is a high storage and high transmission of water. The examples are sandstone, gravel, limestone, maybe fractured, and alluvial. The next type of geological formation is the aquitard. It is a semi-permeable formation that transmits water slowly compared to an aquifer. So here the water movement is limited and the flow is slow. The examples are sandy clay, silty clay, and weathered shale. The next type of water bearing geological formation is aquiclude. It is an impermeable layer that stores water but does not allow movement through it. So there is a negligible flow. The examples are clay, unfractured shale, dense limestone. The next type of geological formation is the aquifuge. It is a completely impermeable formation that neither stores nor transmits the groundwater, so there is neither storage nor the transmission or flow of the groundwater. The examples are compact granite, quartzite, and massive basalt. Now let us see the major aquifer types of India. So here I have listed some of the major aquifer types which are found in our country. So the first and the major aquifer type is the alluvial aquifers. So these aquifers are basically found in the Indo-Gangetic Plain and the coastal belt. And the key properties of these aquifer systems are that these are highly productive with high porosity and permeability and multi-layered system. The next aquifer types are hard rock aquifers. These are basically located in the peninsular India like granite, gneiss, schist. The key properties of these aquifers is that these are having the secondary porosity due to the fractures which are low to moderate yielding. The next aquifer is the basaltic or Deccan trap type of aquifer system, which are basically found in the state of Maharashtra, Madhya Pradesh, and Gujarat. The groundwater in these aquifers are found in the weathered and the fractured zone, which are having a moderate yield. The next aquifer type is the limestone. We sometimes also call it as karstic. These are basically found in the states of Madhya Pradesh, Andhra Pradesh, Rajasthan and Chhattisgarh. So the key properties of these aquifers are that the water in solution channels moderately to high yielding in nature. The next aquifer type is the sandstone aquifer. So these aquifers are basically located in Madhya Pradesh, Chhattisgarh, Rajasthan and Jharkhand. So these aquifers are porous and permeable and having a moderate to good yield. The next aquifer type is the laterite aquifers, and these type of aquifers are basically located in the southern states of Kerala, Karnataka and eastern part of the countries like Odisha and Western Ghats. These aquifers have limited extent and there is a seasonal and shallow water table in these aquifers. The next aquifers are the coastal and deltaic aquifers. So these are basically found in the coastal Gujarat, Tamil Nadu, Odisha and West Bengal. And these are having the moderate yield with saline intrusion, which is a common in these type of aquifer systems. Next aquifer type is the valley fill aquifer system, and this type of aquifer system is more commonly found in the Himalayan foothills and the northeastern states. The key properties of these aquifers is that they are having moderate yield and these are recharged by the river and the rainfall in that particular region. The availability of groundwater in a particular area is affected by the different properties of aquifer. So here we will discuss some of the important properties of aquifers which affect the occurrence of groundwater in that region. So the first most important property of an aquifer is the porosity, specific yield, specific retention, coefficient of permeability, transmissibility, specific storage and storage coefficient. Now let us see the first property, that is the porosity. So porosity is the ratio of the volume of voids or the pore spaces in the rocks or soil to its total volume, which is expressed in percentage. So there is primary porosity, which is formed during the rock formation. The example is the sandstone, and there is also secondary porosity, which is developed with time later on due to the fracturing of the rocks, faulting or solution channels. That is the example is the limestone and the basalt. The significance of the porosity in the groundwater is that it determines the groundwater storage capacity of an aquifer. So high porosity doesn't mean high permeability. However, it depends on the pore connectivity. So here you can see that I have shown that the total porosity, suppose for any geological formation, is 30%. So the effective porosity may be 15%. So the remaining 15% is retained by the aquifer formation or geological formation. So only 15% is the effective porosity. Also, I have listed here the different types of geological materials and their porosity. So here you can see that the gravel is having the comparatively higher porosity as compared to the fractured rocks or clay and silt. So as the size of the particle increases, the porosity increases. The next important property in the groundwater is the specific yield and specific retention. So what is specific yield? Specific yield is the portion of the groundwater that drains freely from a saturated soil or rock under gravity. It indicates the usable water from a well. However, the specific retention is the portion of water that is retained behind in the pores by the molecular and the capillary forces after drainage due to gravity. So the amount of water which is retained is not available for extraction and further usage. If you see the significance of these two properties, the specific yield indicates the groundwater available for use. So higher the specific yield, more is the groundwater available for utilization. And specific retention, it affects the recharge and the soil moisture storage. So higher is the specific retention, it shows that that particular formation is having a good potential for recharge, as well as it will store soil moisture sufficiently. So here you can see that if we sum these two properties, that is the specific yield and specific retention, we will get the porosity. So the addition of specific yield and specific retention is the porosity. Here also I have shown the different materials and their porosity with specific yield and specific retention for your reference. The next important property in the groundwater is the coefficient of permeability. The coefficient of permeability is a measure of the ability of a rock or a soil to transmit the water under unit hydraulic gradient. The coefficient of permeability is sometimes also called as the hydraulic conductivity. It is usually expressed in centimeter per second, meter per second, and meter per day. So the significance of the coefficient of permeability is that it determines the aquifer yield, recharge rate and seepage. The key parameters for the groundwater modeling and well design. So I have also listed here the different types of materials, earth materials, and the coefficient of permeability in meter per second. So here you can see, as the size of the particle is increasing, the permeability is increasing. So it is directly related to the size of the particles which is present in that particular geological formation. The next important property in the field of groundwater is the transmissibility. Transmissibility is the rate at which the groundwater is transmitted through a unit width of the aquifer under a unit hydraulic gradient. It represents the total water transmitting capacity of an aquifer section. The significance of transmissibility is that it indicates the aquifer productivity, it determines the well yield and drawdown behavior, and it is also used in pumping test analysis and groundwater flow modeling. Here I have listed some of the different types of aquifer type and the transmissivity in meter square per day for your reference. The next important property in the groundwater field is the specific storage. So specific storage is the volume of water released from or taken into storage per unit volume of a saturated aquifer per unit change in the hydraulic head. It represents the elastic properties of the aquifer and water. The significance of specific storage is that it governs the storage and the release behavior of confined aquifers, and it is used in the groundwater flow equations and aquifer testing. It is a key parameter for predicting the drawdown and recovery in wells. Here I have listed some of the important aquifer types, that is the unconfined aquifer and the confined aquifer and their specific storage in per meter for your reference. The next important property in the groundwater is the storage coefficient. The storage coefficient is the volume of water which an aquifer releases or stores per unit surface area per unit change in the hydraulic head. It represents the storage capacity of an aquifer. The significance of a storage coefficient is that it determines the amount of water that is stored or released per head change, and it is also essentially used in pumping test analysis and groundwater flow modeling. So, higher the storage coefficient, so greater the storage and slower is the drawdown. Here I have listed the different types of aquifer type and their storage coefficient. So you can see for the unconfined aquifer and the confined aquifer, the storage coefficient and how the water is released from this type of aquifer system. So mainly in unconfined aquifer system, the water is released by the gravity, that is we call it as specific yield. However, in case of confined aquifer, the water release mechanism is different and it occurs due to the elastic compression of the water and the aquifer matrix which is present in the geological formation or the aquifer. So, coefficient of permeability is an important property for determining the groundwater recharge. So, here I am discussing with you some of the important tests which we conduct or perform to measure the coefficient of permeability of that particular geological formation. So basically we can classify these methods into laboratory test, field test and indirect methods. In laboratory test, which is basically based on the Darcy's law, that first is the constant head permeability test, which is suitable for the coarse grained formation or the soil. Next one is the falling head or the variable head permeability test, which is suitable for the fine grained soil. Further, we also use the field test, that is the pumping out test and the pumping in test, and in case sometimes if some types of indirect methods are also used for the measurement of coefficient of permeability of a soil, which is based on the computation based on the particle size of that particular geological formation, and also computation based on the consolidation tests. So here I have given the two figures which shows how the constant head test and the falling head test is performed in a soil laboratory to measure the coefficient of permeability of a soil. Let us see an important law which is used in the field of groundwater, that is the Darcy law. So Darcy law describes the flow of groundwater through porous media, stating that the discharge rate is proportional to the hydraulic gradient and the cross-sectional area of flow. Here we have some assumptions also. The first assumption is that the flow is steady, laminar and saturated medium, is homogeneous and isotropic, with temperature and viscosity remains constant. The significance of this Darcy law is that it is the foundation of the groundwater flow analysis and it is used to estimate the seepage, recharge, wear yield and hydraulic conductivity. So here it is the equation, that is the Q is equal to K multiplied by A multiplied by I, where Q is the discharge or flow rate in meter cube per second. K is the coefficient of permeability, that is in meter per second, and A is the cross-sectional area of flow in meter square, and I is the hydraulic gradient or change in head per width distance. Now let us see that what is artificial groundwater recharge. So artificial groundwater recharge is the intentional process of augmenting the natural recharge of groundwater using the man-made methods to increase the aquifer storage and improve the water availability in the geological formations beneath the earth's surface in the saturated zone. So why artificial recharge is required? Artificial recharge is required to enhance the groundwater levels in the depleted areas, to store the excess runoff or the surface water which is available in the form of either rainfall, runoff, or it may be the canal water. Sometimes we do artificial groundwater recharge to prevent the saline water intrusion, especially in the coastal aquifers or the coastal areas of the country. The other important function of the artificial groundwater recharge is to reduce the flooding and also to prevent the soil erosion. Now let us see some of the key factors for effective artificial groundwater recharge. So first important factor is the site selection. So the selected area which is having the declining groundwater level or overexploited aquifers should be given preference. And generally we prefer gentle slopes and permeable soil or rock formation, example sand, alluvium, etc. And generally we avoid areas with impermeable clay or high contamination risk. The second important factor is the geological and the hydrogeological conditions. The adequate aquifer thickness and permeability is an important factor which should be considered for artificial groundwater recharge. The presence of unconfined or semi-confined aquifers is also an important factor for effective groundwater recharge. The availability of storage space within the aquifer is also important. The third key factor is the source of water which is available and its quality. Before going for an artificial groundwater recharge in a particular area, it should be ensured that sufficient quantity of surplus water or treated wastewater is available for artificial recharge. Further, the quality of water which is available for artificial groundwater recharge should be free from any type of impurities like toxic substances, heavy metals, sediments, etc., which can contaminate seriously the groundwater in the aquifers. Next important factor is the design and maintenance of these artificial groundwater recharge structures. So once we have installed the artificial groundwater recharge structures, it is also essential that we properly design these structures and maintain these structures by desiltation and maintenance to prevent the problems of clogging and reduce in the recharge rate. The next important factor for the artificial groundwater recharge is the monitoring and the management. The continuous monitoring of the water levels and its quality is very important for ensuring that we can go for a successful artificial groundwater recharge. Further, the community participation is also required for long-term sustainability of any artificial recharge process or mission. Now, let us see that what is the significance of artificial groundwater recharge. So, The groundwater recharge leads to the groundwater level improvement. It replenishes the depleted aquifers and raises the water table in overexploited areas. It also ensures the sustainable groundwater availability for irrigation and drinking purposes. The next important significance is the drought and water scarcity mitigation. It stores the excess monsoon runoff for use during the dry periods or the drought. It also enhances the water security in arid and semi-arid regions. Next important significance is the quality improvement. It also facilitates the natural filtration of percolating water through soil, and it also helps in diluting the pollutants and the salinity level, especially in the coastal zones. The another important significance is the control of the land degradation process. It also reduces the soil erosion, flooding, and waterlogging. It also maintains the ecological balance in watershed area. The next important significance for artificial groundwater recharge is the enhanced well yield and reliability. It increases the discharge of wells and boreholes, reducing the pumping cost and the energy requirement. The other important significance is the coastal protection. It also prevents the seawater intrusion into the freshwater aquifers in coastal belts. There are different methods for artificial groundwater recharge. So basically, we classify the artificial groundwater recharge methods into two categories, that is the direct method and the indirect method. In direct method, we are having two further sub methods, that is the surface method and the subsurface method. In surface method, we have ditch and furrow system, stream augmentation, basin or percolation tank, and flooding. In subsurface method, we have dug well, recharge pit or shaft, and recharge well. In indirect method, we have two important methods, that is the induced recharge and the aquifer modification methods. So, the first important method is the surface or spreading method. These methods are suitable where large area of basin is available and aquifers are unconfined with impermeous layer above it. The rate of infiltration depends on the nature of topsoil. If the soil is sandy, the infiltration will be higher than those of silty soil. The presence of solid suspension in water is used for recharge clogs, the soil pores, leading to reduction in the recharge rate. The water quality also affects the rate of infiltration in the surface methods. In surface method, the first method is the flooding. This method is suitable for relatively flat topography. Here, the water is spread in the form of a thin sheet. It requires a system of distribution channels for the supply of water for flooding. Higher rate of vertical infiltration is obtained on areas with undisturbed vegetation and sandy soil covering. The next surface method is the basin and percolation tanks. In this method, the water is impounded in series of basins or percolation tanks. The size of the basin may depend upon the topography of that particular area. In flatter area, will have larger basins. This method is applicable in alluvial areas as well as in the areas with hard rock formation. The efficiency and feasibility of this method is more in hard rock formation where the rocks are highly fractured and weathered. The next important surface method for artificial groundwater recharge is the stream augmentation. When the total water supply available in a stream or river exceeds the rate of infiltration, the excess loss is lost as runoff. So this runoff can be arrested by constructing a series of check dams or by widening the stream beds. Thus, larger area is available to spread the water in the river, which will further increase the infiltration. The site selected for the check dam should have sufficient thickness of permeable bed or weathered formation to facilitate recharge of stored water within short span of time. The water stored in these structures is mostly confined to stream course and the height is normally less than 2 meters. To harness the maximum runoff, a series of such check dams may be constructed in a watershed. The next surface method for artificial groundwater recharge is ditch and furrow system. In areas with irregular topography, ditches or furrows provide the maximum water contact for recharge. So, this technique consists of a system of shallow, flat-bottomed and closely spaced ditches or furrows which are used to carry water from sources like streams or canals and provide more percolation opportunity. This technique requires less soil preparation and is also less sensitive to the silting problems. Now, let us see the subsurface method for artificial groundwater recharge. So, these recharge structures lie above the surface and recharge the groundwater directly through a dug well or a bore well. The important structures commonly used are recharge well and the recharge shaft. So, recharge well can further be classified into two types, that is the injection well where the water is pumped into the recharge and the recharge well where the water flows under gravity. So basically in subsurface method, these are the two important and mostly used technique for artificial groundwater recharge. In subsurface method, the next important method for artificial groundwater recharge is the injection well. The injection well are similar to a tube well and in this technique is suitable for augmenting the groundwater storage of deeper aquifers by pumping in the treated surface water. So these wells can be used as a pumping well during the summer season as well as for the recharge during the excess water runoff availability period. The method is suitable to recharge single aquifer or multiple aquifers. The recharge through this technique is comparatively costlier and also required specialized techniques for handling. Recharge well is an important method for artificial groundwater recharge in the subsurface method category. The recharge well for a shallow water table aquifers of up to 50 meters are cost effective because the recharge can take place under the gravity flow. These wells could be of two types. One is dry and another is wet. The dry types of well have bottom of the screen above the water table. In such wells, the excessive clogging is reported due to the release of dissolved gases and the water leaves the well on the other hand. So there is a need for redevelopment methods have not been found effective in the dry type of wells. The wet type of well are the wells in which the screen is kept below the water table and these wet type of wells have been found to be more successful. The next important method in the subsurface category of artificial groundwater recharge is the pits and shafts. In the areas where impervious layer is encountered at a shallow depth, the pits and shafts are suitable structure for artificial recharge. These structures are cost effective to recharge the aquifer directly. The diameter of shaft should normally be more than 2 meters to accommodate more water. The advantage of shafts or pit structure is that they do not require a large piece of land like percolation tank and other spreading methods in subsurface category. There are practically no losses of water in the form of soil moisture or evaporation like other methods of spreading. In the subsurface category of artificial groundwater recharge, the dug wells are an important structure. In alluvial as well as hard rock areas where there are thousands of dug wells have either gone dry due to the considerable decline in the water level. These dug wells can be used as a recharge structure where the storm water and the other surplus water from the canal structures etc. can be diverted into these structures to directly recharge the dried aquifers. The water for recharge should be guided through a pipe to the bottom of the well to avoid entrapment of bubbles in the aquifer system. In the indirect methods for artificial groundwater recharge, the first method is the induced recharge. The induced recharge is the artificial recharge technique which involves the pumping from an aquifer which is hydraulically connected with the surface water such as perennial stream, unlined canal or lakes. The heavy pumping lowers the groundwater level and a cone of depression is created. Lowering of the water level induces the surface water to replenish the groundwater. This method is effective where the stream bed is connected to the aquifer by sandy formation. In the indirect methods for artificial groundwater recharge, aquifer modification methods is sometimes also used. Here I have discussed two methods in which we go for aquifer modification. The first one is the bore blasting. This method is used to increase the fracture porosity of an aquifer system. The shallow bore wells are drilled in the area where the fracture porosity of the aquifer is planned to increase. These boreholes are blasted with the help of explosive which create fractures porosity in the aquifer, which ultimately leads to increase in the yield of that particular well of that particular area. The next important method of aquifer modification technique is the hydrofracture jacket technique. In the hydrofracturing, it is used to improve the yield of a bore well, and in this technique, the water is injected at a very high pressure to widen the existing fracture of the rocks. The high pressure injection of water also helps in removing of clogging, creates the interconnected pores between the fractures and extend the existing length of the old fracture. In the indirect method for artificial groundwater recharge with aquifer modification, the jacket well techniques is described here. The jacket well technique is used to increase the yield of a dug well, and in this method, the effective diameter of a well is increased by drilling small diameter bores around the well in a circular pattern. The next technique is the pressure injection grouting technique, and this technique is used to control the outflow from an aquifer. So, cement slurry is injected into the aquifer using the mechanical means or manually near to the aquifer outlet like a spring. The next technique is the stream blasting and widening the cracks near the streams and joining them to the lineaments or aquifers so that the water level rises of the retention capacity along the banks of the streams also leads to artificial groundwater recharge. Dear viewers, now we have reached to the end of this presentation. So let us see that what can be the way forward for the artificial groundwater recharge in our country. The first point for artificial groundwater recharge is the integrated management, that is, the conjunctive use of surface and groundwater at the watershed scale. The next point is the scientific planning, which involves the aquifer mapping, real-time monitoring and the GIS-based site selection for the artificial groundwater recharge structures. The next important point is the decentralized recharge. The local structures like check dam, percolation tanks and recharge wells are found to be more effective in artificial recharge as compared to big structures. Based on the experience of working in the watershed, we have found that these small structures can be more effective in inducing the groundwater recharge. The next important point is the urban and the policy support. Definitely there are different types of guidelines from the government, but still there is gap in the implementation stage. We need to have some type of roof water harvesting system so that every drop of water which falls in our country can be saved and properly utilized. For that, there is a need for the strict regulation and incentive based policies so that the people come forward for taking the initiative in the artificial groundwater recharge. The next important point is the community and the capacity building. Sure, there is a need for creating awareness among the rural as well as the urban areas, and there is a need for proper training and participatory program for sustainable recharge. So with this, I thank you all for your patience listening on this topic